All right, hello. Welcome to my channel. This is an educational channel where we go over different, mostly theories of everything, all-encompassing theories that can affect your whole life, um, and you know, really speak to every aspect of life. And we are in the middle of doing a lot of stuff on the reciprocal system of theory. Today is video number 204 on the reciprocal system, and this was a system of theory, or theory of everything, that was first devised by Dewey B. Larson way back starting in about 1930. He eventually worked out his two fundamental postulates in the 1950s, started writing books from there based on a deductive process. So he has his two postulates, takes those two postulates and basically, if this, then that, if this, then that, and develops an entire theoretical universe. So he's basically saying this is what the universe would look like if these postulates were true. And then he compares it to the universe that the scientists had observed and measured. And in 90% of the cases, there is an identical match. In 10% of the cases, the legacy scientists, have been proven wrong, or at least been shown to be wrong. They haven't picked up on this yet. But so that's what we're looking at with Mr. Larson's work. We're looking at his 1979 book called Nothing But Motion. And that kind of encapsulates his theory in general, that we live in a universe of motion. And for Larson, the idea of motion is the relationship between space and time. That sets up a generalized reciprocal relationship between space and time. You can think of motion as basically a fraction, and either space or time is the numerator of the fraction, and either time or space is the denominator of the fraction. But it can be a little bit more difficult because space and time have their coordinate aspects, meaning that they can be multi-dimensional. XYZ coordinates, even in some cases more than 3 dimensions. And space and time, that's what Larson calls coordinate space and coordinate time. And then they have their clock aspects. Clock time. Time is always getting later and later and later. And this is a flow of time, but in no particular direction. It's what Larson calls a scalar motion, a motion that has a magnitude but has no direction. And then we also have clock space, the flow of space. Space is always getting farther and farther and farther apart. And that was observed by the Hubble telescope way back in the 1920s, where they observed that all of the galaxies are moving away from each other, or at least all of the distant galaxies are moving away from each other. And then space and time also have their discrete units only. There is no continuity of space and time. They come in chunks, very small chunks, but chunks nonetheless. And one chunk or one unit of space in one chunk or one unit of time is the speed of light. So the speed of light is basically 1 over 1 equals 1. So the speed of light is 1 in this universe, and then there is a part of the universe, half of the universe, that's moving slower than the speed of light, that Larson calls the material sector. And this is the half of the universe that we're familiar with. And then there is half of the universe that Larson calls the cosmic sector, that is all moving faster than the speed of light. This is the half of the universe that we know very, very little about. But we could learn about this half of the universe because of the generalized reciprocal relationship between space and time. So what we know about the material sector can be extrapolated to the cosmic sector, and all we have to do is reverse the roles of space and time. And you can see that with the coordinate space and the clock time. In the material sector, we have coordinate space and clock time. We see 3 dimensions of space, and we're moving through time, getting later and later and later. But in the cosmic sector, we see 3 dimensions. Well, we do not see it, but there exists 3 dimensions of time and clock space. Space is always getting farther and farther apart. And so you can see that there is just a reversal of the roles of time and space, and that enables you to extrapolate and understand what's going on in the cosmic sector. Larson does that here in this book that we're looking at, Nothing But Motion, especially in some of these later chapters here that we're working on, number 15 right now, called Cosmic Ray Decay. A cosmic ray is basically a cosmic atom. So earlier in the book, he covered atoms, what an atom actually is, and it's basically a combination of several different kinds of motions. At first, you have a photon at the core of the atom that is a simple harmonic motion, which is, in Larson's world, a combination of a translational motion and a vibrational motion at 90 degrees of the translational motion. The combination creates a sine wave or a simple harmonic motion. Now, some of Larson's successors have challenged that, and especially KVK Nehru and also Bruce Perret have said that they believe that the photon actually comes from a birotation, a combination of 2 rotational motions counter-rotating, and that also yields the interference of those yields a sine wave. So that is the model for the photon that Nehru uses. Larson disputed that until he died, but they've done some tests on it, and I think their idea makes a little bit more sense to me, but we will hash that out later on. So as of right now, Larson, in this book, Larson's saying that the photon is a translational motion combined with a vibrational motion going 90 degrees to the translational motion. Now that creates the photon, which is at the core of subatomic particles. When you're talking about an atom, you have 2 photons at the core of those atoms, and then you take those photons and you rotate them, and that's what creates the atom. So an atom has a 3 number rotation of rotations for their notation. And so you have A, B, and C numbers. The first is a primary 2-dimensional rotation. The second is a 2-dimensional secondary rotation. And then the third is a 1-dimensional electric rotation, which is optional. And so those 3 numbers create atoms. Now he's moving into the cosmic sector, and he's determining what's going on with the cosmic atoms. And he's looking at cosmic ray decay, which means that when a cosmic atom comes across the boundary to the lower than speed of light sector, the material sector, which is as a result of a powerful explosion, generally from a star or a galaxy. And then that cosmic ray has to decay because it is not stable in a material environment. And he's pointing out the steps of the decay. Generally, the atoms that come over are generally cosmic hydrogen or cosmic helium, but then they decay up the periodic table until they get to cosmic krypton, which has a notation of 330. And he says that when you're talking about atoms, the max is 440, and so when you flip that 330, you end up with 110, which is equals 2 massless neutrons. So that's the idea for Larson's process of cosmic ray decay, that it starts out from cosmic hydrogen or maybe cosmic helium, decays all the way up to cosmic krypton, and then once it gets to cosmic krypton, it flips over to become 2 massless neutrons, and then those are stable. Okay, we're going to start right here in the middle here, where he just got done talking about decaying the first couple steps of the decay up to C lithium 5. Okay, further increases in the inverse mass of the residual cosmic atom by successive additions of single atomic weight units would be possible, but the probabilities favor larger steps as the material equivalent of a cosmic increment continues decreasing. The 1 unit increment in each of the 2 steps from cosmic helium 3 to cosmic lithium 5 is therefore followed by a series of increments that are uniformly 1 atomic weight unit larger in each successive decay, except for the step between cosmic nitrogen 14 and cosmic neon 20, where the increase over the size of the previous increment is 2 units. On this basis, the 2 1-unit increments that produce C lithium 5 are followed by a 2-unit increment to C beryllium 7, a 3-unit increment to C boron 10, and a 4-unit increment to C nitrogen 14, and then a 6-unit increment to C neon 20. These decay products are not capable of retaining both of the gravitational charges or isotopes. Isotopic mass of their precursors, but they keep one of the charges, and all of the cosmic elements identified as members of this section of the decay sequence have masses which include a 931.15 electron volt million electron volt gravitational increment, as well as the basic equivalent of the cosmic element, which is 1862.3 over the atomic number, a million electron volts. The indicated life of a cosmic atom with 1 gravitational charge after dropping into the range of one-dimensional motion is about 10 to the minus 10 seconds. These theoretical masses and lifetimes are in agreement with the observed properties of the class of transient cosmic ray particles known as hyperons, as indicated in the following tabulation. Okay, so Larson is saying that C lithium 5 is equivalent to the physicist's omega particle, and the Larson calculated the mass of that particle as 1676. According to the physicist, is actually 1673, and the lifetime is 1.3 times 10 to the minus 10 seconds. Then we've got C boron 10. That's the psi particle, Xi, and that's 1304 million electron volts. Observed, that's 1321. And the lifetime is 1.67 times 10 to the minus 10. Then we have C nitrogen 14, which is the sigma particle, and that is calculated by Larson theoretically as 1197 mega electron volts. By the physicist, it is also calculated at 1197 through their observations and measurements. And then the lifetime of that particle is 1.48 times 10 to the minus 10 seconds. Then we have C neon 20. the lambda particle. And according to Larson's theoretical calculations, this should be 1117 million electron volts. And according to the physicist's observations, it is 1116 million electron volts. And the lifetime is 2.52 times 10 to the minus 10 seconds. The masses given are those of the negatively charged particles. Positive electric charges and other variable factors introduce a fine structure into the numerical values of the properties of the particles that has not yet been studied in the context of the reciprocal system. The observed decay pattern is in agreement with the theory, so far as its general direction is concerned. That is, all of the members of the series decay in such a manner that the eventual result is C neon. It is still uncertain, however, whether the decay always passes through all of the stages identified with the normal sequence, or whether this sequence is subject to modification either by omission of one of the or more of the steps, or by a variation in the size of the ejections of time displacement. The C beryllium-7 atom, mass 1463 megaelectron volts, for instance, is not listed in the tabulation, as its identification with an observed particle of mass 1470 megaelectron volts is rather uncertain. This does not preclude its definite identification as a decay product eventually. It may be noted that in this connection that the omega particle C lithium-5 was found only as a result of an intensive search stimulated by a theoretical prediction. However, the fact that the last three members of this Hyperon series, which were the first to be discovered and are still the best known, are separated by only one decay step, suggests that there is little, if any, deviation from the normal sequence in those cases where the full range of decay from C helium to C neon is involved. When we examine the properties of gravitational charges at a later stage of the theoretical development, we will find that the stability of these charges is a function of the atomic number. The mathematical expression of this relation, which we will derive from theory, indicates that the stability limit for a double gravitational charge in the terrestrial environment falls between the material equivalents of C helium-3 and C lithium-5. This accounts for the previously mentioned fact that C lithium-5 and the elements above it in the cosmic series are incapable of retaining two gravitational charges. But the center of the zone of stability for these elements is closer to the +1 isotope, meaning one gravitational charge, than to the 0 isotope, the basic rotation. And for this reason, they are all singly gravitationally charged, as indicated in the preceding discussion. From C silicon 27 upward in the cosmic series, the center of the zone of stability is closer to the 0 isotope, and these elements carry no gravitational charges. So as a result, you don't have to multiply that, 10 to the minus 2 second multiplier into the calculation for the lifetime. And also add in that 931.15 mega electron volt unit for the gravitational charge either. Without the gravitational charge, the mass of C silicon 27, the decay product resulting from a 7-unit addition to C neon 20, is 137.95 megavolts, and the low speed lifetime is about 10 to the minus 8 seconds. The corresponding observed particle is the pion, with measured mass of 139.57 megavolts and a lifetime of 2.62 2.602 times 10 to the minus 8. Pions are frequently reported as products of of observed cosmic ray events initiated by primaries. As we will see in the next chapter, such production is quite feasible where there is a violent contact of some kind with the release of a large amount of energy. But direct production of pions in decay is not consistent with the decay pattern as derived from theory. The apparent direct production is, however, understandable when the relative lifetimes of the pion and the earlier decay products are taken into consideration. There is no reason to believe that normal decay in flight will result in any change of direction. Ejection of massless particles will take care of the conservation requirements without the necessity of directional modification. Because the entire decay process up to the production of the pion occupies only a very short time compared to the lifetime of the pion itself, it is unlikely that the usual methods of observation will be able to distinguish between a pion and a cosmic particle undergoing a complete decay to the pion status in flight. Okay, I think we're going to stop right there. Now, have heart, because this is probably one of the most difficult chapters in Larson's entire oeuvre, and it's very theoretical. Like I said yesterday, I've read this chapter multiple times, and this is the first time that I've even understood any of it. So I'm excited for myself, but for you, you may have to listen to me go over this chapter multiple times before you get it, and you might have to consult the physics textbook to kind of figure out what the scientists are saying. But what's important here is that Larson is basically taking on the entire scientific establishment. There are thousands of scientists that are trying to understand this, and Larson is able to figure out by himself, with his reciprocal system of theory. Okay, have a great day. We'll see you next time.